Good morning, students. Today we will start our chapter number 13, magnetic effects of electric current. Okay, in the previous chapter on electricity, we have learned about the heating effects of electric current. Okay, we have seen how the current flows in the conductor due to the flow of the charge per unit time and how it produces the heat in the conductor, and that heat we use in the different appliances, and we have studied the heating effect of electric current. Now we are going to study in this chapter about the magnetic effects of electric current. Okay, how this flow of current produces the effect of magnet. Okay, so what could be the effect of electric current? This is the other effect other than heating. This is known as the magnetic effect. Okay, so here in this diagram, a compass needle is given here. Okay, and is deflected on passing an electric current through a metallic conductor. Okay, if this compass needle, it is a magnetic compass. If this is held in an electric circuit, we have discussed in the chapter 12. This is electric circuit consisting of the variable resistance, a source, a cell or an ammeter, okay, key. So compass needle is deflected on passing an electric current. So what it shows? It shows that the electric current produces the deflection in the compass needle, and this gives us the that the this magnetic effect comes from the electric current. Okay, so electric current through the copper wire has produced a magnetic effect. Thus we can say that electricity and magnetism are linked to each other. They are both linked to each other, and the reverse possibility of electric effect of magnet is also true. Okay, in this chapter we will study the magnetic fields and such electromagnetic effects. Okay, we will study about in this chapter about the electromagnets, electric motors and magnetic effects of electric current. Okay, and electric generators also is we have to study in this chapter, but due to the reduction in the syllabus, that is 30% syllabus reduction, electric generators are removed from this time. Okay, this time we don't have to study about the electric generators, AC and DC. So rest of the topics like electric motors, magnetic effects, electromagnetic inductions, these topics we have to study. So who was responsible? The scientist who is responsible for studying the electromagnetism was the Hans Christian Ørsted. Okay, one of the leading scientists of the 19th century. He played a crucial role in understanding the electromagnetism. Okay, and in 1820 he accidentally discovered a compass needle. Okay, he discovered that a compass needle got deflected when electric current passed through a metallic wire. Okay, this observation Ørsted showed that electricity and magnetism were related phenomena. Then his research later created technologies such as radio, TV and fiber optics. Okay, with the help of this research on electromagnetic effects, so the other devices, useful devices, radio, TV and fiber optics were discovered. Okay, so unit of electromagnetic field strength is named as the Ørsted in his honor. Okay, magnetic field strength unit is Ørsted in his honor. So first topic is our magnetic field and field lines. Okay, so compass needle get deflected when brought near a bar magnet. Okay, we are familiar with this, that whenever compass needle gets deflected and brought near a bar magnet. Compass needle is in fact a small bar magnet. What is a compass needle? Compass needle is a small bar magnet. Okay, and the ends of the compass needle point approximately towards north and south directions. Okay, a bar magnet has also two poles, that is north and south poles. Okay, and the compass needle have also two poles, that is north and south directions exist. Okay, the end points toward the north is called the north seeking or north pole, and the other end that points toward the south is called the south seeking or south pole. Okay, through the various activities we have observed that The like poles repel while unlike poles of magnet attract each other. Okay, when we can using the other magnets. Okay, now the two like poles when we brought together, then they will get repel. Okay, and when we brought the unlike poles of the magnet towards each other, then they will get attracted. Okay, here iron filings are showing a pattern of these field lines. Okay, our topic is field lines, so if you want to see the field lines, we will spread these iron filings on a white paper and then placed a bar magnet around it. Then we will see the pattern of the magnetic field lines. The iron filings will get distributed in the form of the field lines. Okay, you can see here the field lines through the bar magnet shows us the uh, uh, direction of the magnetic lines from north to south inside the bar magnet, and outside it is south to north. Okay, so this is the magnetic effect of moving charge. Here the charge get moves due to the placing of this bar magnet. Iron filings will act as a charge and this will move. Okay, this will form a pattern. The magnet exerts its influence in this region. This shows that it has some magnetic field around it and it has some magnetic field strength around it. Okay, and the iron filings get experience a force, and this force thus exerted makes iron filings to arrange in a pattern. Okay, so the lines along which the iron filings align themselves represent magnetic field lines. Okay, the lines along which the iron filings align themselves represent the magnetic field lines. So how we can see the magnetic field lines? This is in the form of the region surrounding a magnet in which the force of magnet can be detected. Okay, it's said to have a magnetic field, and the lines along which the iron filings align themselves, that is the line, are the visualization of this magnetic field. Okay, therefore they are known as the magnetic field lines. Okay, so by taking a small compass and bar magnet, we can also show the deflection and formation of the field lines. Okay, draw a magnetic field line with the help of a compass needle. Here we can make the magnetic field lines. These are the field lines around a bar magnet. Okay, you can see here from inside the direction of the field lines are from north to south, and from outside the field lines are from south to north. Okay, so here these are the field line diagram. It is an important diagram, field lines pattern on a bar magnet. Okay, and magnetic field, what is magnetic field? Magnetic field is a quantity that has both direction and magnitude. Okay, and the direction of magnetic field is taken to be the direction in which a north pole of the compass needle moves inside it. What is the direction of this magnetic field? Is taken to be the direction in which a north pole of the compass needle. Okay, we will brought here a compass needle and see the deflection. Wherever the compass needle shows the north pole, move inside it. Okay, so therefore it is taken by convention. The field lines emerges from north pole and merge at south pole. Okay, emerges from north pole and merge at south pole. Okay, inside the magnet. Okay, inside the magnet emerges from north pole and goes toward the south pole, and the direction of field line is from south to north. uh, South to north is outside the bar magnet. Okay, so here you can see these convections. The magnetic lines, field lines, are closed curves. Okay, these are closed curves, and these closed curves, no two field lines, what are the properties of these field lines? They never cross each other. Okay, if they did, it would mean that the point of intersection, the compass needle would point towards two directions. This is not possible. You can see here they never intersect each other. Okay, these field lines, and they are crowded field lines. Okay, represents strong field. The number of field lines, more the dense the number of field lines, more the strength of this magnetic field. Okay, and it forms continuous closed curves. Okay, it forms continuous closed curves, and it has both magnetic magnitude and direction, and tangent at any point gives us the direction of magnetic field. Okay, so if you place any point here in the field lines and mark a tangent on that point, then it will give us the magnetic field at that point. So magnetic field due to a current carrying conductor is our first topic. Is the next topic after magnetic field lines. So magnetic field lines creates a deflection, a pattern. Okay, and we have seen that electric current through a metallic conductor produces a magnetic field around it. So how we will see this magnetic effect? Okay, here in the diagram you can see the deflection of the compass needle. Okay, simple electric current in circuit, straight copper wire is placed parallel to and over a compass needle. The deflection in the needle becomes opposite when the direction of current is reversed. Okay, so whenever a straight wire or straight wire carrying conductor in the form of concentric circles around it with center on wire, it has a direction of current, and depends on the strength of the magnetic field. The current depends on the strength of the magnetic field. Okay, what determines the pattern of the magnetic field generated by current through a conductor? Does the pattern depend on the shape of the conductor? Okay, so here we can see a straight wire conductor forming the circular pattern. The magnetic field lines here are in the form of circles. Okay, variable resistance, pattern of concentric circles indicating the field lines of magnetic field around a straight conducting wire. These arrows circle shows the direction of the field lines and a close-up of the pattern of time. So what happens to the deflection of this compass needle? Okay, this deflection is due to the flowing of the current along this straight conductor. ठीक है, straight conductor में से जब भी current pass होगा then will show the deflection in the needle. Okay, and what happens to the deflection of the needle if the compass is moved from the copper wire but the current through the wire remains the same? To see this, now place the compass at farther point from the conducting wire. What change do you observe? We see that the deflection in the needle decreases. If we place the compass at a distance from the circuit, away from the circuit, then the deflection gets decreases. Okay, whenever we connect it to the circuit, the deflection will increases, and when we place it at a far point, then so it can be noticed from this activity. The concentric circles shows us the field lines, magnetic field lines. Okay, and it shows us represents the magnetic field around a current carrying straight wire become larger and larger as we move away from it. Okay, so whenever we put the compass needle away, the magnetic field will become larger, forms the larger concentric circles. Okay, so this is our first lecture. Here we study about the magnetic field lines and the first effect of the current in the straight conductor. Okay, the magnetic effect on the straight conductor. We will see a pattern like this. Concentric circles are formed in the form of magnetic field. Okay, so it has a particular direction which is given by the Fleming. We'll discuss in our next class the right hand Fleming's rule and left hand Fleming's rule, right hand thumb rule and right hand Fleming rule, and left hand Fleming's rule. So different rules are there for uh, determining the direction of the current. Okay, so this is we have to study in our first lecture.